Welcome. Today's notes worksheet is entitled Rational Exponents. By rational, what we mean is a number that can be written as a fraction of two integers, kind of like this. And so what we're going to be seeing all the way through the notes worksheet is really fractional exponents. We're going to start out with a little investigation. You're going to need your calculator for this one, and it's nice and simple here. It's just different ways to represent a calculation, and all I'm looking for is just a yes or a no. Are they the same? So why don't we go ahead and start that out here. I'm going to bring my calculator up if you can get yours. And let's go ahead. It looks like initially I'm going base 5. And I'm going to take that base 5 and raise it to the 1/2 power. Now it wouldn't make too much of a difference here, but get in the habit of raising these fractional exponents inside the parentheses. So 5 raised to the 1/2. And there we go. We get a nice looking decimal like that. And what I want to do is very simply compare it to the square root of 5. So I'm going to hit second square root and 5, and notice we get the exact same number right there. So as again, just as simple as it gets, are they the same? And yeah, that's the case. So 5 to the 1/2 is equivalent to the square root of 5. Let's move over to part B. 12 to the 1/3, here's your fractional exponent or rational exponent. How does that compare to the cube root of 12? So I'm going to bring my calculator up again and do exactly that. So 12 raised, and then let's go 1 divided by 3, and we get that number right there. Keep an eye on that number if you would, because now I'd like to take a look at the second representation, which would be the cube root of 12. If you've never seen cube root before on the calculator, here's how we pull it off. Go under the math menu for me, and you'll notice it's about the fourth one down there, and so cube root 12, and notice we get the exact same thing. So when we take 12 and raise it to the 1/3 power, that is equivalent to saying the cube root of 12. So a yes on that one, please. Let's confirm it just one more time. Here we go, our fractional exponent right there, base 18 on this one. So here we go, 18 raised, and I'm going to go ahead and get those parentheses going again to the 1/4, and notice we get that value right there. How does that relate to the 4th root of 18? So in this case, again, you're going to have to get comfortable finding these on the calculator. To do a 4th root, as a matter of fact, we actually hit the number 4 first. So hit that number 4, then go under math, and do you see that, sort of that x root right there? I think that's the one we're looking for. So now we're telling the calculator to do a 4th root of 18, and there we go. And notice, of course, it's the same. So 18 raised to the 1/4 is the same thing as the 4th root of 18. Two different representations of the same calculation. So we're ready for our conclusion 1. I'm just going to throw it in for any base. And so fractional 1 over a number, really that denominator represents the root of our term. That would be the nth root of our base, basically. So hopefully that all clicks nicely there before we move on to the second piece. Okay, so I'm going to go on to D and E and F. The only difference here is now I'm going to include a numerator other than 1. And so I'm going to do 10 to the 2/3. There's my rational exponent right there, and relate it to radical form right over there. So let's go ahead and do that piece. And this one you do have to be extra careful on. Parentheses around that 2/3, please, if you would. So 10 to the 2/3. Nice, I get that decimal right there. Now let's go ahead and compare that to the cube root of 10 squared. And so I'm going to go back to my math menu. Please do the same. There's the cube root. So cube root 10, let's get that. And let's go ahead and square it. And notice we get the exact same. All right, so we can start talking about what the denominator of our fractional exponent means, and now also what the numerator of our fractional exponent means. I'll tell you what, why don't we skip E for just a moment, and let's go into F. I like that one. So let's do 3 to the 7/4, and then compare that to the 4th root of 3 to the 7th. So here we go. Bring up my calculator, probably for the last time here. 3 raised, 7 divided by 4. Got it. There it is. Keep an eye on that decimal if you would. Now everyone, I'd like the 4th root, so hit the number 4. go under Math, and there it is, the x root. So the 4th root of 3 raised to the 7th. And notice we get the exact same thing. Awesome. So here we go. A yes on that. And just FYI, if we did it on letter E, it would have worked out as well. Perfect. And so you can kind of see where the numerator fits in terms of our radical form right here. And let's go ahead and put this in place. So algebraically, here's what I wrote. A to the m over n. So now numerator, denominator of our fractional exponent is equal to the nth root of a to the m. That looks really nice. So you can see the denominator represents the roots. Let's go ahead and put that in. In fact, I'm going to go ahead and draw that in right here. So the denominator is the root. And for lack of a better description, the numerator is what we raise it to. And that's exactly what I'll have you put right there. Hope that makes pretty good sense based on this. I hope you kind of see all that together. Now just one thing to note here in terms of this piece. This looks fine. We would read this as the nth root of a to the m. Theoretically, and you can write this or not, it's totally your call, but the order doesn't really matter how I do this. So this would mean the same thing, by the way. So I could take a to the m first, then do the nth root, or I could do the nth root first and then raise it to the m. So either way there, again, if you don't want to write this piece, it doesn't matter. These two mean the identical thing. All right, that looks great. So why don't we back it up with just a couple examples here. So I'm thinking 1 and 2 should suffice, and then we'll get into some exponential properties with this. It would be great, actually, if you can kind of beat me to it or pause or I don't know, whatever you want to do here. But very simply, the top 3 in example 1 are in radical form. Please convert them to exponential form. The bottom 2 are in exponential. Please convert them to radical. And so, you know, almost it's like a race here. Let's do it. So square root of 15, that would be 15 to the 1/2. So again, square root and raised to the 1/2 power mean the identical thing. That comes up a lot, so just please keep that in mind. This would be the 2nd root, obviously mostly called the square root. So 15 to the 1/2. Next one, cube root. So this would be 30 to the 1/3. Nice, just move it along. It looks like I've got a base 7, and I'm raising it to the 3rd and taking the 4th root. So 7 to the 3/4. Those would be exponential form of those 3 numbers. 2 different representations. Now just reversing the process here, 22 raised to the 2/3. So the bottom number is the root. So something like that would suffice. Again, if you want to go ahead and sort of do this, and I'll just leave that up to you, cube root of 22 and then squared means the same thing. I would probably say you see this one a little more often, but again, no worries whatsoever, either way. And then this one here, of course, is going to be the 6th root, 2 to the 11th. And that looks good. All right, so hoping everyone is comfortable with those pieces, just going from one to the other, what the numerator and denominator truly represent numerically. Bottom number is the root, top number is what we raise our base to. So why don't we put the calculators aside for a moment or two, and as it says, simplify each expression, no calculator. So let's see if we can pull this off. Let's see if we can derive a little more meaning behind these numbers. So what does 9 raised to the negative 1/2 power, what is it actually equivalent to? Well, we've done this before, of course, where we have dealt with negative exponents, so why don't I do that up here? To deal with that negative exponent and make it positive, give it a little more meaning, let's do our 1 over. So 9 to the negative 1/2 is really 1 over 9 to the 1/2. And then we could probably go one step further here, of course. What is 9 to the 1/2 power in the denominator? Well, what we saw, of course, is the bottom number is the root, so the 2nd root of 9, or the square root of 9, and square root of 9, of course, is 3. So, long story short, if you were to type in 9 raised to the negative 1/2 power on your calculator, it should be 1/3. Okay, good. Let's see if we can pull off this one. 16 to the 3/2. So let's kind of think about this in a couple different ways. But if I'm going to do this without a calculator, I have 2 options. I either can take 16 and begin to raise it to the third, or I can bring it on down a little bit and take the second root, or the square root of 16. Now, 16 raised to the third is a little difficult to do just mentally, so I think it's easier to kind of break this on down. I do know that the square root of 16 is 4. And so when I do that, I change the base to 4, and all I have to apply is that top number, which is what I raise it to. And so 16 to the 3/2 at this stage would be 4 to the third, and 4 to the third is 64. If you don't need this intermediary step right here, please feel free to skip it. Mentally, I would just think to myself, square root of 16 is 4, 4 cubed is 64, and get right to here. So long story short, try to take the root first, then raise it to the number. It's a little easier, I believe, to do. Okay, well, let's do this next one right here. So same deal, kind of combining these two together. In this case, negative exponent, first order of business. Let's bring it on down. So it's going to be a 1 over. And again, just mentally think about what's easier. Do you want to raise 27 to the second power and then take the cube root of that? Or is it easier to think of taking the cube root of 27 and break that on down, a smaller number, and then square that? And I think it's doing exactly what I just said. So I'm going to say take the cube root of 27, which happens to be 3, and then square 3, and that would be 9. And so as a result, should be 1/9. Good. So example 2 there, A, B, and C, just working with the fractional exponent and understanding what each part means. Bottom number is the root. I would take that first, then raise it to whatever power after you change that base. Let's move on to example 3. And so we've got a set of 5 here, and I think what we'll do is just apply all of our exponential properties that we've been working on. Now obviously the exponents get a little harder, but I think we can work through this and navigate it appropriately. So here we go. Simplify each expression, and it looks like for example A, I kind of put these both in parentheses, but I'm not really raising it to anything, so I don't know. I'm actually going to take it out of the parentheses. Just a little cleaner for me visually, and so something like that. And this is all just multiplication, as we can see. And we all know, just in terms of multiplication, that is commutative, so I can just change the order and combine what I can combine. So I'm thinking 5 times 7 is 35. So why don't we go ahead and just multiply those two numbers together. And then I'm thinking about multiplying these two powers base x. Now remember how we do this, of course. Good little review. When we multiply powers of the same base, we keep the base and we add the exponents. And of course at this stage, the only difficulty lies in the fact that these are fractional exponents and we just have to add fractions. So 1/2 plus 3/4, get a common denominator. So I'm thinking of this as 2 over 4 plus 3 over 4. And so when I multiply powers, I keep the base and add the exponents. 2/4 and 3/4 would make 5/4. And I'm liking that as a final answer. I wouldn't really do much with that. I guess the argument can be made if the example was given in exponential form, then what do you say we write our answer in exponential form? If our problem is given in radical form, why don't we go ahead and answer in radical form when we get there? Let's do part B. So same deal. It looks like in this one, I'm not really raising this to anything, so I'm going to remove that. I like doing a little y to the first on that one, by the way. And then I do have to remove the parentheses here and apply this raised to the 1/2. So remember, power to a power. We multiply those exponents together. -2 times 1/2 is -1. So x to the negative first. And then y just raised to the 1/2. So I'm hoping you would agree that when I remove those parentheses, especially on that second one, that this is what I get right here. Okay. Now again, we can multiply powers that do have the same base. So what do you say we go ahead and do that? I'm going to go ahead and multiply the powers base x. And when I multiply powers with the same base, I keep that base and again add those exponents. 2 over 3 plus -3 over 3. That's what -1 would be. So 2 over 3 plus -3 over 3 is negative 1 over 3. So x to the negative 1/3. And in times, let's go ahead and do the same on the base y. Keep the base, add the exponents, 2 over 2 plus 1 over 2, and there is my nice rational exponent right there. I'd go maybe a step further. I'm going to bring this on up, and the y to the 3/2 is looking great. What do you say we bring this on down, and we get that piece right there. Good. So 2 different examples, and just applying the exponential properties that we've developed before. Let's do C. So I see a couple options on C. I'll run them by you, and you can choose whatever you want. I guess initially we could take each term to the 1/2 power. That is perfectly legitimate. Or we can simplify inside the parentheses first, kind of consolidate those bases, then raise it to the 1/2 power. I guess, your call what you want to do. I'm going to simplify inside the parentheses. That's just what jumps out at me. So, the 9, really not much I can do with that. But I am going to go ahead and divide these 2 powers of base x. And so this is good practice right here. How do I divide powers of the same base? Well, I keep the base and I subtract the exponents. So in this case, 2 minus 1/3. And remember how this works. 6 over 3 would be the number 2. So 6/3 minus 1/3. So I'm getting that to the 5/3. Not too bad. So again, hopefully you saw that piece and getting x to the 5/3 right there. Let's repeat, and if it helps, I'll put that in place. Y to the 1/3 divided by y to the first. Keep the base, subtract the exponents. 1/3 minus 1, or 1/3 minus 3/3. And hoping you would get that piece right there. All right, now I simplified inside the parentheses a touch. It is time, of course, to raise that to the 1/2 power. And so let's go ahead and do exactly that. 9 to the 1/2, I believe we've seen this before. Basically, that just means the second root, or the square root of 9. So 9 to the 1/2 is 3. Now here we're going to have to be just a touch careful. Power to a power means that we multiply the exponents together. So 5/3 times 1/2. And if it helps you, again, I'll erase this momentarily, but this is what we're doing. And, we've seen these operations before. Try to cross cancel, nothing there. So just multiply across. 5 times 1, 3 times 2. I'm getting 5 over 6. Okay, good. Same thing over here, everyone. Let's do that with the base y. So power to a power means I multiply those exponents. So negative 2/3 times that 1/2. Again, just trying to be visual for you here. If you can pull this off quicker, please feel free to do so. I would cross cancel on the 2's, and I'm getting y to the negative 1/3. Looking good. I'd probably clean that up just ever so slightly. What do you say we do a 3, x to the 5/6, and that y to the 1/3 comes down, looking great, and there's our final answer. Okay, so A, B, and C got somewhat progressively harder there, but you can see really not too bad. D and E, different form. Let's see what we can do with it. So I'm kind of looking at letter D, and I'm trying to do cube root of 2 times 4th root of 2. I don't think we've seen this type of situation when we talked about properties with radicals. And you don't have to write this down, but we saw this, square root of 2, square root of 3. That is square root of 6. As long as it's the same root, we can multiply what's underneath. Adding together, same thing. It kind of had to be identical. This would be something like that. I mean, we saw that too, but I don't think we really saw much that dealt with this scenario right here. So let's find a way around it. So this form, this radical form here, nothing's really jumping out at me. I don't really know what to do with it. But I know that there is a different way to represent that number. Cube root of 2 is, as you can see, 2 to the 1/3. And then wait a minute, 2 to the 1/4 would be equivalent to the 4th root of 2. And is that something that we can work on? Yeah. So again, you're just seeing some nice connections here between the two different forms. This form, not very user-friendly, but by changing it, well, all of a sudden something comes out. So now I can multiply powers with the same base. I do keep the base, and I add those exponents. So everyone, what do you say we do 1/3 plus 1/4? Get a common denominator. I'm thinking a common denominator of 12 should do the trick. So this would be 4/12 plus 3/12, and I like 7/12 there. Check that out if you get an opportunity. Now, if you left this as a final answer there, I can certainly live with that. That would be fine. I just kind of figured that since this was written in radical form, we should go ahead and write it in radical form. Good practice there, of course. So how does the 12th root of 2 to the 7th sound? If you actually wanted to do 2 to the 7th as 128, you could see the base does change, and this would be the 12th root of 128. So again, just different expressions. Nice. Letter E, I think, follows in the same vein here. Let's see what happens. Not much I can do here, guys, as is, but let's see what we can do when it's at least written like this. So exponential form, and actually I look at this in exponential form, and nothing does jump out at me right away, except for the fact that I can probably change one of these bases here in order to make it look like the other base. And it's up to you how you want to do this, but the thing that jumps out at me is that 4 is really just 2 squared. So it's almost like this. This is what I'm thinking, at least, is trying to write those both in base 2. And it's like, oh, okay, well, 4 to the 1/3 would be the same as 2 to the 2/3. 2 times 1/3. And then 2 to the 1/2. So something like that. I hope that kind of works and then follows the same procedure as letter D. So I'm going to multiply those together by keeping the base and adding the exponents. Fractions, guys, so common denominator here is definitely 6. How does 4 over 6 plus 3 over 6? So 2 to the 7/6. And again, I'll just kind of come up here in terms of radical form. And the only reason I kind of say that is because it was already in radical form. Something like that would do. Again, if you want to change that base, that's fine. Great. So I'm hoping that front side now makes pretty good sense dealing with both representations, and it's pretty clear as how that plays out. Let's go look at the back side. And so the back is going to be more a prelude for tomorrow's lesson. We're going to see some pretty complex expressions tomorrow, dealing with some pretty difficult numbers. So what I'd like to do is just a little prelude to that and develop just a little foundation. So kind of bear with me on this piece and just know that it really allows us to move forward nicely tomorrow. So one of the things we're going to be looking at tomorrow is working with the greatest common factor. And so what we're going to do is just take a look at a little number theory here, I guess, what is called prime factorization, to find the greatest common factor of any two terms. And then we'll try to develop a quick conclusion from that. So here we go. Watch how it plays out if you can. If I asked you what the greatest common factor of 24 and 16 is, you would probably, without second guessing yourself, you'd probably say 8. And that's great. You can write the answer 8 there. What I'd like to do is just show you a way to kind of get that using what's called prime factorization. And so what we're going to do is create a little tree diagram here, and we're going to break down the number 24. So guys, give me 2 branches if you would. If you do it slightly different, that's fine, but 2 and 12. 2 is prime, so please circle it. 12 goes further. 2 times 6, which should work out here, circle the 2. 6 goes further, and so 2 times 3. And so basically, the short version of a long story here is that this 24 can be written as a product of 4 prime numbers, 2 times 2 times 2 times 3. Hope everyone's okay with that. Now 16, let's follow it in a similar fashion here, is 2 times 8. Let's go a little quicker now. 2 times 4, 2 times 2. Does that sound all right? And now what we're looking for, as it kind of suggests, take the common prime factors from each list. And that's what greatest common factor is all about. Greatest, meaning we take all of them, Common, meaning it has to be part of both our tree diagrams. So I guess the way I would see it is I see a number 2 as a factor is common to both lists. So let's take a 2. I see another 2 is common to both lists. So let's take another 2. And I see a third 2 is common to both lists. So I take a third 2. Is there any other factor that happens to be common to both lists? No. And guys, of course, what's 2 times 2 times 2? And there's your answer. Kind of cool. All right, so nice and concrete initially. We'll get a little more abstract with this in just a moment. What do you say we run this by pretty quickly here and see if we can get letter B? If I asked you for the greatest common factor of 12, 18, and 36, you would all tell me 6. So let's go get it using this prime factorization method. I'll be rather quick. Break it down with me though. 2 times 6. 2 times 3. There is your prime factorization of 12. 18, guys, let's knock it out. 2 times 9. 3 times 3. Okay. Now if I want the greatest common factor of all 3, I need the factors that are in both lists. So I'm just going to go 2 and 18. I'm going to go 2 and 9. I'm going to go 3 and 3. So is there a number that happens to be in all 3 lists, all 3 circled tree diagrams? Well, I see a 2. It's there, and it's there, and it's there. Let's take it. What else is there? I see a 3. It's there, and it's there. Is there anything else that is common to all 3 lists? And I guess at this stage, the answer is no. Here's a 2, but there's no 2 in this list. Here's a 3, but there's no 3 in this list. And so as a result, you see, 2 times 3 is 6. All right, now I hope everyone's okay with that development there, because now let's get a little abstract with it. And let's see if we can draw a conclusion, which again should shortcut a couple things going forward. If I asked you to do the same thing here, you would tell me x squared is really just x times x, right? Circle them. If I asked you for the prime factorization of x cubed, well, we just do 3 branches. Really, it's just x times x times x. So now if I asked you for the greatest common factor of those 2 terms, you would see what's common to both, and you'd say, all right, there's an x in both lists. Let's take it. There's another x in both lists. Let's take it. And that's all that's common to them. And x times x, lo and behold, is x squared. And so what you see, everybody, is that the greatest common factor of these 2 terms is x squared. Now we'll come back to this in a more concrete manner in just a second. But I need you to visualize, if you would. What if I did the same thing on these 2? What do you think the greatest common factor would be? Well, I'm hoping you're starting to see that when I'm dealing with any 2 powers of the same base, the greatest common factor is very simply the lower of the 2. So in this case, it should be x to the 5th. If you can envision 5 arrows right here, 7 arrows right here, and taking the 5 that are here that are also here, there's your greatest common factor. And that's what we need to kind of take care of. So let's do this conclusion and then just come back to it for a moment and then wrap this notes worksheet on up in the next couple minutes. So the GCF, which again is coming back with a vengeance on the next notes worksheet. The greatest common factor of powers is the smallest degree of that base. So please keep that in mind, because the exponents are going to get pretty difficult. But if we keep this in mind, we have a way to navigate through it. Okay, before I get into the last example there of the day, let's just go back to this for just a second. So basically, I told you that the greatest common factor of x squared and x cubed is x squared. And, you know, I mean, it played out exactly that. Let's get concrete with this and just see it in action. So let's pick a number here and put it in for x. So let's say I pick 2. 2 squared, everybody, is 4. 2 to the third is 8. What if I asked you for the greatest common factor of 4 and 8? Well, the largest number that divides into 4 and 8 happens to be 4. There it is. All right, what if I did 3? 3 squared is 9. 3 to the third is 27. What if I asked you for the greatest common factor of 9 and 27? Well, the greatest common factor happens to be 9. Are you starting to see it? One more. 4. 4 squared, 16. 4 cubed, 64. What is the largest number that divides evenly into those two? It's 16. No matter what number I pick, it's always this value that is the greatest common factor. And I hope you see that. Cool. Well, let's go do the last piece. So just want to get comfortable with factoring. The top two are ones we've definitely seen before. And notice the bottom two, and this is where it's going to lead into tomorrow's notes worksheet, even quite a bit more complex than what you see. So let's start it out there. Greatest common factor. So just kind of think about this term and this term. I think 12 and 18. I'm hoping you would all pull out a 6 as the greatest common factor. And what is the greatest common factor of x to the 4th and x to the 6th? Well, the conclusion kind of speaks for itself, guys. It's just the smaller power. So it's x to the 4th. And so now what we want to do is just be careful. Make sure you understand what goes in here. We'll talk more about that on the next notes worksheet. But 6 times what would give me 12? 2. And I already pulled all of those out, so there they are. Put a plus in between. 6 times what is 18? Let's put a 3 in. And then this is a good one. X to the 4th times what would be x to the 6th? And I'm hoping you see it would be x squared. And you kind of think about this in terms of factoring. We pulled out 4 factors of x, and so of course there are 2 factors of x remaining. And that's greatest common factor. Nice. Let's continue. This one is just a review from grouping, as a matter of fact. We saw this when we did a lot of grouping. But basically I see 2 terms, and notice it's just the same base. The x plus 3 just happens to be the same power, so it just all gets pulled out. So I'll pull out the x plus 3. When I pull it out of here, I'm left with x squared. Let's do our plus. And again, we've seen this before. When I pull it out of there, I'm left with the 5. So want to get comfortable kind of seeing what is the remaining factor or parts to that factor after we pulled out the GCF. All right, now C and D. So again, title of the notes worksheet, Rational Exponents. Now what we're going to do is try to factor this expression right here. We're going to manipulate it. We're going to rewrite it in its factored form. So what is the greatest common factor of x to the 2/3 and x to the 1/3? Well, again, don't overthink. It's just the lower power. So x to the 1/3 is the greatest common factor. And now what I need to do is just kind of figure out, I'm going to do this just once here, what would go back in the blanks. If I pull out x to the 1/3, there needs to be something right here. If I pull out x to the 1/3, there needs to be something there. All right, well, let's think about this. X to the 1/3 times something would give me this. And I would multiply powers. And when I multiply powers, they have to have the same base because I would keep the base. And what do I do to the exponents when I multiply powers? I add the powers. I'm sorry, I add the exponents. So 1/3 plus what would give me 2/3? Well, 1/3 plus 1/3 is 2/3. Good. If I made you distribute this in, would I get this piece right here? Sure. If I pulled that whole thing out, what's left? 1. And so that's our final answer. Again, I'm just going to get rid of those blanks that you see down on the bottom there. But basically, we did it. Cool. Again, they're going to get harder, quite a bit as a matter of fact. But we're going to develop some good ideas around that. Right now, just preliminary steps. Okay, let's go get D. 2 terms. What is the greatest common factor of those 2 terms? The lower power, x to the 1/4. That's lower than x to the 1/2, so we pull it out. Now what goes here? Plus, and then what goes here? Same deal. I have to multiply these 2 things together in order to get this. So keep the base and add the exponents. 1/4 plus what is 1/2? Well, 1/4 plus 1/4 is 2/4, which is the 1/2. And then I pulled this out, and there you go. Again, we'll talk about some more definitive ways to get these terms inside. We'll really lay it out in a very, very definitive and concrete manner for you, and hopefully that'll help. But for right now, nice and straightforward there. Hopefully you're able to work with those rational exponents for the time being. You could almost flip the page and take a look at some of the expressions we're going to see coming up, because again, they do get quite a bit more intricate. Well, why don't we wrap that up at this stage? Definitely take a look at that front side, make sure it makes really good sense, and please let me know how I can help with anything. Thanks for listening.